Hello. In the previous lecture, as you're aware, we were doing complex functions, and we had just started with the complex functions, and we were doing a little bit about single valued functions and multi-valued function. And in this line, we were actually trying to find the principal value of some functions. For example, actually, I gave you a few questions, so I hope you must be aware of whatever we have done so far. So we've already established that logarithmic function is a multi-valued function. So in order to restrict its value to the principal value, we restrict the argument to the principal argument, and then we write that particular value as the principal value. So I left you with two of the questions, and so I'll start my session with those questions at first, and then we'll see what next can be done. So let us see. So 1 plus iota raised to power 1 plus iota. We wanted to find the principal value of this. So we wanted to find the principal value of this particular, whatever you can say, is a complex number. Okay. So 1 plus iota raised to power iota. So how to find this? See, as I mentioned, whenever you have some alpha belongs to C, okay, and let's say we want to write z raised to power alpha, then what would be z raised to power alpha? You can as well write this as e raised to power, sorry, alpha log e, sorry, e raised to power alpha, and here you can write z. So this is how also you can write, provided z is a non-zero complex number. So it is a non-zero complex number, then you can write this way. Because always remember, it's not that log x is not defined at x equal to 0. That's not the case. Always remember, even log z is not defined at the origin, that is z equal to 0. So why? Because at z equal to 0, it means what? It means it is equal to 0, comma 0. And if you remember, what is log z? Log z is nothing but it is equal to log of modulus of z plus iota argument of z, if you remember. And then this is mod z is what? It is equal to log of root over x square plus y square. This is a real valued function. Please remember. Now, if x is equal to 0, y equal to 0, so it will not be defined. So kindly remember, even log z is also not defined at z equal to 0. Please do remember, this is not single zero. It is an ordered pair here. Okay. So z raised to power alpha is equal to e raised to power alpha log z. And then what you can do, you can simply write this value of what? This log, which is equal to log mod z plus iota. You can write argument of z, and then you can play with things. You know that what is argument of z. I've already established that argument of z in general can also be expressed in terms of the principal value. And in order to generalize it, you can multiply, add some to imply, because there are all sort of possibilities because of the periodicity of time function. So this is how you do. I have already explained all these things. So today I left you with this question. We wanted to find the principal value of 1 plus iota raised to power 1 plus iota. So what I have to do, I'll simply write e to power 1 plus iota, and then I'll write log of 1 plus iota. Okay. So basically what will happen, this will give you all these things. We'll also discuss in detail when we are going to separately, I'm going to teach you some functions like exponential function, sine, cosine function, trigonometric, logarithmic function. We are going to again see them all over again, but right now just take them as they are, okay? So that you are going to learn a few things. So what it would be equals to 1 plus iota here, and then what is log of 1 plus iota? It will be log mod z, so it will be root 2 plus iota. And now, in order to write the principal value, we are going to restrict it to the principal domain. What is the principal argument? What is the principal argument of 1, 1? It is pi by 4. Remember. So 1, 1 will lie in the first quadrant. I told you in the first quadrant, the principal argument is simply given by tan inverse y by x. So this will be okay. So ultimately, the principal value of 1 plus iota raised to power 1 plus iota is e raised to power 1 plus iota, and then you have this entire stuff which is log of root 2 and then you can write plus iota. So this is how you write things. Okay, this is how you write things. Then I also gave you another question that was this one. That is, I think what it was. It was to find the real part of. We wanted to find the real part of. We wanted to find the real part of principal value of. We wanted to find the real part of principal value of 4 raised to power 4 minus of iota. So we wanted to find the real part of principal value of 4 raised to power. So what it will be equal to? It will be equal to e raised to power 4 minus iota, and here I'll write simply log 4. So it will be equal to e raised to power 4 minus iota. And what is log 4? You know that what is 4? 4 means it is purely real. So if it is purely real, then we know that for such values, the argument, even the principal argument is 0. So principal argument for real values is simply 0. Okay, so this will come out as log 4 plus iota 0. Okay, and ultimately what we get e raised to power 4 minus iota into log of 4. Okay, and then I can simply write it as e raised to power 4 log 4 times into e raised to power minus iota log 4, and which certainly would give you, this would be e raised to power, this would be 16. Sorry, not 16, 4 raised to power 4, whatever 4 raised to power 4 is, I think it would be 16 to 16, that is 256. And then you have this e raised to power minus iota, so this will be equals to cos log 4 minus iota sine log 4, right? Now what we are supposed to find, we want to find the real part of the principal value of this. We want to find the real part of principal value of e raised to power 4 minus iota log 4. So what do you think the principal real part would be? It would be simply this. So the real part is equals to 256 times cos of log of 4. I hope it is clear. So this is how you do some questions. Most of them we have done already. Okay, so most of them we have already done. So you can, I think you are in now in a situation. We are now in a situation that we can take our study to a next level. That is, we are going to today study limits, continuity, and differential. Limits and continuity at least, and then we are going to study analytic functions, so on and so forth. And now one must be excited that we have started the complex analysis part. So first, before starting limits, let me define a few more things that were left yesterday in complex functions. So first, let us discuss a few more concepts regarding complex functions. And then we'll start with limits and continuity at least today. Okay. So we've already seen that a complex function is nothing but it is an ordered pair of real numbers. So yesterday we were doing this. So we knew what is fz. Fz can be written as ux comma y plus iota vx comma y, where both of these are real valued functions. So basically fz, so basically u is nothing. If f is defined from some a to, let's say, c, then we know that u is defined from a to r. And uxy is another one real valued function. Another real valued function is this. And what is ultimately f? F can be expressed as ordered pair of these two real valued functions. So obviously they will be contained in R square. Okay. So similarly, like when we were studying complex number, we were writing that a complex number is nothing but an ordered pair of real number. Similarly, in complex analysis, the first thing we study is, sorry, this belongs to R square. First thing that we study is complex functions, and complex functions are nothing but they are the ordered pair of these real valued function. I already told you there are two possibilities. See, if f is a rule which assigns every value of z, of z to w uniquely. Okay, if f is a rule which assigns every value of z to w uniquely, where z is in the plane of domain of definition and w, okay, so w is in another plane. If it expresses, if the rule expresses, if the rule assigns every value in the domain of definition to a unique value in another plane, which is a w plane I have written here, then we'll write that these functions are single value. Otherwise, the functions are multi-value. So one of the important function, logarithmic function here happens to be a multi-valued function. We may restrict it to a single valuedness by restricting the argument. But if we don't restrict the argument take infinitely many values. So logarithmic function is an infinite multi-valued function. And what we also found that z raised to power n, if n belongs to, in fact, this and even this, if n belongs to z or n belongs to n, then this is a single valued function. But this function itself becomes single valued if n does not belong to z. Then it becomes a multi-valued function. As an example, I showed it multi-valued function. As an example, I showed you n equals to half. Okay. So I hope it is clear till now. Now, okay, now let us discuss what is 1, 1. So you know all these things from your standard 12, but still now, since you're starting with complex analysis, so I'm writing everything. Okay, so if fz1 is equals to fz2, then it should necessarily imply that z1 is equal to z2. Or if z1 is not equal to z2, then it should necessarily imply that fz1 is not equal to fz2. If this is the case, where z1 and z2 belongs to some complex, to the set of complex numbers, then we say that our mapping fz, let's say w is equal to fz, is a 1, 1 mapping. Then we say that our mapping fz is a 1, 1 mapping. Okay, what is open mapping? I hope I have already explained you open sets, so now there is no worry. What is an open mapping? A mapping is said to be open mapping if it maps open sets to open sets. So if a mapping set maps and a mapping, if a mapping maps open sets to open sets, then that kind of mapping is called as the open mapping. But that mapping must be onto. Okay, so that mapping must be onto. And I know what is onto. You know that if I'm defining, let's say if range of f, let's say if f is defined from a to b, and if range of f is completely equal to this b set, then the mapping is said to be onto mapping. Then the mapping is said to be onto mapping. Or very traditionally, when we say function, okay, so we can also say very traditionally that for every element in set V, one must have pre-image in set A. If that is the case, then also the mapping is on. So a mapping is said to be open mapping if it maps open sets to open set onto Y's, or it maps open sets onto open sets. Okay, you can write this also. It maps on open sets to open sets. Only then you are going to say open mapping. And open onto, you already know that if the range of function is completely equal to this particular set, then we say that this is an onto mapping. Or for every element in set B, you have a pre-image in set A. Then we say that the image is onto. Then you say that function is onto. Now, let us see another thing. What is inverse? How would we define inverse? So we know that we are mapping a function from Z to W. So we are mapping a function from Z to W, that implies fz is equal to W. Then we can also write that Z is nothing but F inverse W. Okay. So for every element in W, if you take an inverse, then you can find the element in Z plane such that Fz was equal to W. This is called as inverse of F. This is referred to as the inverse of F. This is referred to as inverse of F. Okay. Okay. Now, in complex analysis, at times another word is used instead of 1, 1. So instead of 1, 1, at times another word is used which is called as univalent. Okay, so if somebody says univalent or if somebody says 1, 1, they are one in the same thing. Okay, and we'll see later on that if a function is univalent at some point z naught, a function is said to be univalent at some point z naught if it is univalent in the neighborhood of z naught. So we'll see all these intricacies later on. But right now, just understand univalence or univalent means 1, 1. Okay, so let us say if you are defining an inverse image, then the prerequisite is that your function must be univalent. Your function must be univalent and function must be onto. So both 1, 1ness and onto-ness are required for defining the inverse function or inverse function. So let us say inverse I have already defined. Now let us say that function is defined from R to A. Yeah, here R is what? Here R is the domain of definition. Okay, that is f z is equal to W. Here Z would belong to R, which is certainly subset of C, and W will belong to A, which is certainly a subset of C. If this mapping, okay, if this mapping uh, is a kind of 1, 1 and onto, then we can always define an inverse image. Then we can always define an inverse of function, that is f inverse W is equal to Z. Okay. Okay. So this is one thing. A function is a constant function. You know what is a constant function? if it assumes only one value on the entire complex plane. So in fact, if you're defining it for something, let's say from A to B, that function we define from A to B, where A is a subset of C and B is a subset of C, function is said to be constant if B contains only one element, that is C. Okay, for all Z belongs to A. So for all Z belongs to A, if fz is equal to C, that is if the set B contains only single point, that is C, then we say this kind of mapping is a constant mapping or the function is constant function. I hope it is clear. This is simple. And the function is said to be bounded. A function is said to be bounded if there exists some m such that fz mod is less than m, where m is some positive real number here. And what is fz? For all z belongs to A. So for all z belongs to A, if fz mod is less than m, then we will say that the function is bounded on this particular domain of definition A. I hope it is clear. Now with regards to univalence, let us take some example. Let us take some example and let us take some simple example. Fz is equal to z square. And we have to see whether it is univalent or not. So if I take fz equal to z square and let us define the domain of definition to be equal to mod z less than equal to 1. So clearly the domain of definition is what? So domain of definition is simply a closed disk. So I already have referred to you what is a closed disk. So it is a closed disk, or you can write it as it is a closed disk centered at 0 with radius 1. Okay. So what would be the range of range of f? So range of f would also be equals to closed disk only. Clearly, the range of f would be also closed disk because fz is equal to z square, then fz mod will be equals to what? So fz mod will be equals to z square mod, which is equal to mod z whole square, and certainly which is less than equal to 1. So range of f is also less than equal to 1. So range of definition, range of function f is also the closed disk only. Now, how this mapping is going to work? So if I consider this as z plane, and let us say this is your closed disk centered at 0 with a radius 1. Okay, so let us consider the z plane where we are having this closed disk centered at 0 and radius 1. And if I take any points from this particular sector with angle alpha, so if I take any points from this sector, how are they going to map? They're going to get mapped to another plane, which is the W plane. But the point is this, if I take any points from this particular area, then obviously I can write this way. So I can write this way that let us say R is one only e ki power iota alpha. And if I square it up, what will happen? All these points are going to get mapped in an annular region, but now with angle 2 alpha. So all these points here are going to map here, are going to get mapped. Okay, are going to get mapped here. Okay, is that clear? So clearly, an annular region with vertex at 0 or with center at 0 of alpha radians is going to get mapped to another region with angle 2 alpha. Okay, so under this particular mapping, that is fz is equal to z square, this will be one of the consequences. Now we have to see whether this is univalent or not. So one easier way is to see like directly, but I would suggest you to literally ponder it a little bit on it. So let us say that I take z is equal to r e ki power iota theta, where r obviously lies between 0 and 1, because inside the points will have radius less than equal to 1 only, and theta can assume all the values. So let us take okay, so let us take theta to be in in a certain range. Okay, so let us take that theta to be in certain range. Okay, so let us take theta to be in range from 0 to 2 pi. Okay, so let us take theta to be in the range 0 to 2 pi. So now if I am writing fz, which is equal to what, z square, it implies what? It implies some r square e की power 2 iota theta. Let us say if I want to compare it in W plane. So in W plane, if I write any complex number equivalent to, let's say, rho e की power iota phi, then clearly rho must be equal to what? R square, and phi must be equal to what? 2 theta. So what would be the range of phi? Phi would lie between 0 to 4 pi. Fine. Now let me take two values. See what I'll do. I'll take two values. I'll simply take e raised to power iota theta and another value of complex number, another complex number I'm going to take, that is, let's say, and you just take r also, where r obviously lies between 0 and 1. So we are taking a complex number z1, which is r e की power iota theta. Obviously it lies inside the circle. And another value, let's say r e की power iota theta plus 2 pi. Now this is certainly a different value. Why it is a different value? Because you know that if I'm writing r e की power iota theta plus pi, it is equal to r e की power iota theta into e की power iota pi, and you know e की power iota pi is negative, so minus r e की power iota theta. So z, and which is equal to certainly minus of z1. So clearly z1 is not equal to z2. Now if z1 is not equal to z2, then the mapping is univalent if fz1 does not come equal to fz. Now, what would be z1 ka square? Z1 ka square would be r square e की power iota 2 theta, right? And what would be z2 square? Z2 is what? Minus z1. So it will be minus z1 whole square, which is simply z1 square, and which is simply r square e की power iota 2 theta. So clearly, fz1 is equal to fz2. Z1 was not equal to z2, but fz1 is not equal to, sorry, is equal to fz2. It implies that f is not univalent. Fz is not univalent. This is something that you should understand. Okay. However, if you restrict the domain, if you restrict the argument, then things may work. What if we restrict theta or simply argument? Okay, then things may work. Why? Because you have to understand that only if I can make, only if I take numbers z1 and z2 such that argument differs by pi, only then it may work. This kind of scheme may work only if I take two different complex numbers, and what kind of difference does it have? There should be a difference in argument by at least pi. So this is what we have seen. So what I'll do, I'll restrict my argument in such a way. So what I'll do, I will consider a domain D, the subset of C. And what is D? D contains all the points inside the closed disk. But the point is this: I'm going to only take argument from 0 to pi. So I'm going to take only argument in 0 to pi. Okay. So now if I take z from here, then I know that z square would be simply r square e की power iota 2 theta, and simply it is equal to, let's say, if I say rho e की power iota phi, so I know that rho is equal to what? R square, and I know phi would be equal to what? Now since argument, that is theta, lies between here to here, so phi would lie between 0 to 2 pi. Now no value cannot be repeated. No value can be repeated. Every value would come only once. Now every value would come only once. Now question arises, if I want to prove it, that no such. So question arises, can there not be two pre-images for z square? Can there not be two pre-images for z square? This question arises. Then obviously, let us take, I know that this what would be the pre-image? So I know that z square is nothing but it is equal to some rho e की power iota phi. Here phi is equal to what? 2 theta. And I know theta lies between 0 and pi. And I know that rho is equal to r squared. If at all, there are two pre-images, when can there be two pre-images? Two different pre-images? There can only be two different pre-images. I'm writing here. There can be only two different. There can be only two different pre-images if Z1 and Z2. Argument of Z1 and Z2 differs by pi. And we have already restricted our argument, that is theta, in such a manner that it is less than pi. So clearly we arrive at a contradiction. So you cannot have two pre-images. You cannot have two pre-images. So restricting a domain is a certain strategy to make a function 1, 1 here. Otherwise, it would have not remained 1, 1. Very simply, we could have also done it. So let's say I've already taught you what is 1, 1 or univalent. So univalent function or 1, 1 function is, if I'm writing that Z1 is equal to Z2, if I'm writing Z1 is not equal to Z2, then FZ1 should not be equal to FZ2. And if I'm writing Fz1 is equal to Fz2, then it should necessarily imply that Z1 must be equal to what? Z2. If this is the case, then I'll say that my mapping is 1, 1 or univalent. Now, if I'm saying my mapping is Fz is equal to Z square, is it a 1, 1 function? No, it is not. Because see, if Z1 square is equal to Z2 square, it means what? It means either Z1 should be equal to Z2 or Z1 should be equal to minus of Z2. Okay. So therefore, this is not univalent. This is not univalent. Okay, so this is not univalent. Now, here, one thing you need to observe, that the point Z1 is equal to minus Z2. Now, what is minus Z2? Let us say if I'm writing the point x comma y here, where would be minus x comma minus y? Here it would be. Right? So if x comma y is here, minus x comma minus y is here. So clearly, if Z1 is this point, Z2 would be this point. Because Z2 is what? Minus Z1. So this particular Z1, Z2, which are related this way, are symmetric about origin. This is symmetric about origin. These are symmetric about origin. Isn't it? So this Z1, Z2 are symmetric about origin. So we can write the points Z1 and Z2 are symmetric about origin. That is, they lie at the same distance from the origin. They lie at the same distance from the origin. Okay. So only when can you make Fz is equal to Z square a univalent function? You can make it a univalent function only if the domain does not contain the symmetric points. If it contains a symmetric point, then it will not remain univalent, because if it contains symmetric points, so Z1, the symmetric point is Z2, and this Z2 is what? Minus Z1. If it contains a symmetric point, the image will be the same. Okay. Okay, so this particular function Fz is equal to Z square can remain univalent if and only if it does not, if and only if the domain of definition, does not contain even a single, symmetric point with respect to origin. Even a single symmetric point with respect to origin. Otherwise, I mean, then it will not remain univalent anymore. So if this is how things may be asked. Also, you can create a univalence if you don't consider the entire circle. So for example, Fz equal to Z square can be made a univalent if you just consider upper half. So it can be made univalent if you just consider the upper half. So let's say upper half means what? All those elements in Z such that imaginary part of Z is greater than 0, or you just take the lower half. Then also, your function is univalent. Okay, so this is how things are. What about fz is equal to z bar? What kind of mapping does, what kind of result this mapping does? So you know that the effect of this mapping would be what? I've already taught you in the first class itself, but again I'm writing it up. So if you have a point x comma y, what will be the effect of z bar? So if this is z, what would be z bar? Z bar would be simply x comma minus y. So this would be your z bar. So what is the effect of mapping? So if function or transformation z bar is done, then the point z bar is nothing but it is the reflection by on this particular real axis. So this is equivalent to writing fz is equal to z bar. This the effect of this mapping is reflection of z about the real axis. About real axis. We have to see whether this function is 1, 1 or not. So whether this function is 1, 1 or not. So clearly, if I take fz1 is equal to fz2, it is equal to what? It is equal to z1 bar equal to z2 bar. And z1 bar is what? Let's say it is x1 minus iota y1, and it is, let's say, x2 minus iota y2. It implies that x1 must be equal to x2, and it implies that y1 must be y2. It implies what? It implies z1 has to be equal to z2. Clearly, this is a 1, 1 function. Okay. And what is it an onto function? Yes, it is an onto function because fz is equal to z bar. So if this is your plane, let's say z plane, and let's say we are taking all set of complex numbers, all finite complex plane we are considering here. For every point, let's say this is x comma y, it is going to get mapped here, x comma minus y. So for every point, you have a pre-image. For every point in z bar, or you can say w plane, you have a pre-image in the z plane. So clearly, this is an onto image, onto plane. Sorry, this is a onto function. Sorry, this is an onto function also. Because no, it is going to cover entire. If z is complete C, then for every number you can always find a z bar. Z bar means what? If you are giving me x comma y, I'll simply do what? I'll take your y and I'll simply do x comma minus y. So for every x comma minus y, I will have x comma y. So for every point in this w plane, I will have a point in z plane. So clearly this is an onto function also. This is a 1, 1 or univalent function also. Therefore, fz equal to z bar is invertible also. And what is inverse of this particular function? If w is equal to z bar, then z is equal to w bar. So basically f inverse z is again z bar only. So inverse also exists. Inverse of this particular mapping also exists. This is something that you've already done, but just since we are discussing functions, so I'm discussing all these things in detail. What about fz is equal to mod z whole square? What about fz is equal to, if initially let's say mod z only. Let us take mod z only. So what it is going to do? If I take the entire z plane, so if I take the entire z plane here, I take any point on this entire z plane. Okay, so basically I'm going to take all z such that mod z is less than infinity. So I'm talking of the finite complex plane. So I'm talking of the finite complex. If I take any value, mod z is going to do what? Mod z is just going to do it root over x square plus y square. And this is a complete real valued form. This is complete real value. This is complete real value. So what it is going to do? All the points it is going to take and it is going to just map it on the non-negative part of the real axis. It is going to map it on the non-negative part of the real axis. So what this mapping is going to do, fz is equal to mod z, it is going to map all the points of the finite complex plane to the non-negative part of the, why non-negative? Because 0 is one possibility, non-negative part of the real axis. Is going to map all the points in the z plane to the non-negative part of the real axis. Is that clear?
Yes, sir.
Okay, chalo ji. So next is a few definitions, and then limits. I think we'll be able to continue tomorrow only. So limits and continuity tomorrow we'll do. Please revise this lecture before attending that lecture. Otherwise, a few things you may not get. So you know what is symmetric and anti-symmetric till now we have already done, but still I'm writing. A domain D is said to be symmetric. A domain means a domain D is said to be symmetric with respect to origin, is symmetric with respect to origin when it is symmetric if for every z belongs to D. If for every z belongs to D, there is a point, there exists a point minus z belongs to D. So if there is a point z belongs to D, then there should be a point minus z belongs to D. If there is a point z belongs to D, then there should be another point minus z belongs to D. So we'll say that this particular domain itself is symmetric. Okay. This is number one. Now, okay, so this is one thing. A function f. Now, another definition, please do write. A function f defined on domain D, and if this domain D, which is symmetric with respect to origin, so if domain D is symmetric with respect to origin and a function f is defined on this domain D is said to be even, Matlab that what is a domain D? A domain D which is symmetric with respect to origin means what? It will contain the point z also, and it will also contain the point minus z. So if it contains both the points z and minus z, then the function is said to be even if fz is equal to f of minus z, and it is said to be odd if f, this is something that you already know, f of minus fz is equal to f of minus z. So minus of fz is equal to f of minus z. So if your domain is symmetric, then you can define two other functions, that is even and odd. If fz is equal to f of minus z, then the function is even. If minus fz is equal to f minus z, then function is odd. I hope it is clear. All these things, I mean, these are just basic things that you usually do. Why I'm writing all these things? See, when you started your real analysis, at least calculus wise, in your standard 12th, all these things were written. So therefore, I'm just trying to make it as basic as possible. Uh, Solving gate question, net question, they are not that difficult. Once you know everything in great detail, then you can do all those things. Although I'm going to do all those things, but I'm just mentioning that these lectures, I'm trying to cover as much as basic as possible so that even if you are not having a background in complex analysis, then also you can learn it by your own, or at least the self study from book become very easy. Once you do this, then take any book, then you all the even if you want to self study this topic, then it will become very easy for you. So these are the definitions for even and odd. I think these are something that you already. I'm just starting with the definition, and then we'll take this definition tomorrow. So limits, as you're aware, that if I'm saying that limit z tends to z naught, fz is equals to L, what does it imply? It implies that fz tends to L as z tends to z naught. as z tends to z0, fz tends to L. And tends to means what? The distance between fz and L can be made as small as possible whenever distance between z and z0 can be made smaller. Okay, so this is how do we write this particular definition given epsilon greater than 0. You just give me an epsilon because you are saying that function tends to L. Function tends to L means what? The distance between function and L can be made as small as possible. Now, any such terminology as small as possible is very informal. Okay, so you need to give me some epsilon. So once you give me an epsilon, I will produce, for every epsilon, there must exist some del. So I'll produce a del such that fz minus L mod is less than epsilon whenever z minus z naught mod is less than del, and for right reasons, I will also make it greater than 0. Why greater than 0? Because there may be a possibility that function may not be defined at z naught. Function may not be defined at z naught, and there may be a possibility that therefore we are finding the limit. I'm not saying that the limit cannot be found for the function at the point where it is defined. It may be found, but why would one want to find a limit? Possibly function may not be defined at point z0. So therefore, I'm resorting to the deleted neighborhood of z0. So this is nothing but deleted neighborhood of z0. Please understand, what does it mean? It means you are trying to make, let's say this is your z0. You're trying to make a circle around z0 of radius del, but not including z0. Because if you include z0, then z0 minus z0 mod is equal to 0. And so z0 will not be contained. So this is at times referred to as the deleted neighborhood, or I have also mentioned punctured disk at z0. Okay. Am I audible right now? Okay. But not audible. So again, I'm saying, what does limit means? If I'm saying limit z tends to z0, fz is equal to L, it implies that fz will tend to L as z tends to z0. Now these tend to and all those things, like what does it mean? The distance between function and L can be made as small as possible if z, and distance between z and z0 can be made small. So these as small as possible, small doesn't work in mathematics. So you need to give me something. So if you tell, okay, distance between fz and L can be made less than some epsilon, you give me some tolerance limit, let us say epsilon. If I am in a position to give you a del such that fz minus L, whenever it is less than epsilon, then z minus z0 is less than 10. Matlab, whenever you are giving me some, whenever you are saying that you give me some epsilon, then fz and distance between fz and L, I can make less than epsilon whenever z and distance between z0 and z can be made less than del. If for your epsilon, I'm in a position to produce a del always, then I will say that function's limit is L. Am I clear or not clear?
Yes, sir. Clear.
Okay, so again, please pay attention to this concept because this will come time and again, time and again, time and again. And I've seen people struggling here time and again, time and again, and time and again. Be it real analysis, be it complex analysis, everybody doesn't want to, nobody wants to get into this definition. And the core is that everywhere, any question, if you're going to get stuck, you're going to get stuck with this basic definition. So please do understand all these things. First thing, whenever you are going to define limit, we are going to talk of something called as a deleted neighborhood. First concept is this. Why a deleted neighborhood? So if I'm defining a limit at z0, why I'm interested in deleted neighborhood? Because possibly function may not be defined at z0. Let us say sine z upon z. If I'm interested in finding limit z tends to 0, what makes me so interested in finding the limit at z tends to 0? Because I know that function is not defined at 0. Please do understand, I'm not saying that function, I'm not saying that we cannot find limit of a function at a point where function is defined. We can obviously find, but most generally we'll have to write the definition of limit on deleted neighborhood. Okay, this is the first concept. Now, the second concept is, what does limit mean? why there is a need to find a limit? So there may be a possibility that function may not be defined. So we are finding a limit. So let us say that as z tends to z naught, function tends to L. Tends to L means what? If I'm writing tends to L as z tends to z naught, what does it mean? It means the distance between function and the limit, fz and limit, can be made small. And how do we define distance? Fz minus L mod less than epsilon. So we cannot say the distance between fz and L can be made as small as possible when distance between z and z naught, excluding z naught, can be made less than del. We cannot say, because what is as small as possible? So for a mathematician, you need to define a certain limit, a tolerance limit. Let us say you say that function and L, and you ask to me that whether the distance between function and the limit can be made less than epsilon. Let's say epsilon is something like 10 to the power minus 12. And if I'm in a position to give you a del, what is del? If I'm in a position to dictate you that, okay, just take all these complex numbers in this particular area, this particular region, which is z minus z naught mod less than, let's say, 10 to the power minus 6. If I'm in a position to say that if you're giving me 10 to the power minus 12, my del appears to be 10 to the power minus 6. So for every given epsilon, if I'm in a position to give you a del such that fz minus L mod is less than epsilon, whenever z minus z naught mod is less than del. So for your given epsilon, if I'm in a position to give you all those elements z, such that the distance of z and z naught is less than some del, and obviously I'm writing greater than 0 because I don't want to include z naught. If I'm in a position to give you a region, okay, every time you give me an epsilon, every epsilon, and this epsilon is arbitrary, for any arbitrary epsilon which is greater than 0, if I'm in a position to give you a del, how? Fz minus L modulus is less than epsilon whenever z minus z naught is less than 10. So you give me something, I give you every time something. So for example, if I say, let us say, how I will give you some example and then possibly you'll be able to understand. But please understand this definition is quite important. So whenever you are saying that function in L distance can be made as small as possible, it means you need to give me some tolerance limit. You cannot work with as small as possible. What is as small as possible? Nothing. So you tell me, okay, I want that function and L, the distance between function and L can be made less than epsilon. So okay, I'll say, okay, it can be made less than epsilon, but z minus z naught should be less than some del. So for every time you give me an epsilon, and if I'm in a position to give you a del, and obviously I'm not using z naught here, I'm not taking z naught, so I have to define greater than z naught here. But please pay attention here. If you are giving me epsilon and I'm in a position to give you a del, every time you give me an epsilon, for every given arbitrary epsilon, if I'm in a position to give you a del, I would say that this means that limit z tends to z naught, fz is equal to L. This is what you mean by limit. And this is what is the epsilon del definition for the limits. Epsilon del definition of the limits. Otherwise, you know sequences also. You know the sequence also. So if I'm saying that for every sequence Zn converging towards Z naught, if f of Zn converges towards L, then it implies limit fz z tends to z naught is equal to L. So this is the sequential definition for limit. And this is if and only if, that is limit z tends to z naught fz is equal to L if and only if for every sequence Zn which converges towards Z naught, fZn must converge towards what? L. Then we'll say that limit Z tends to Z naught, fz is equal to L. So this is the sequential definition for the limits. I hope it is clear till now.
Yes, sir.
Okay, so this is it for today. We're going to continue from limits, continuity, and differentiability. Just wanted to introduce to you this particular concept. And then we'll see the most important part of this particular functions. Initially, the first, you can say, section or theme is analyticity. So we have to reach analyticity and do some very important discussions on entire functions and also on Cauchy-Riemann conditions, harmonic functions, and so on and so forth. But it requires you to make a certain certain base. Otherwise, you won't be able to sustain there. I hope you're going to get all these things now. Just read it and just let me know. Okay. So